Good morning, class. Today we're going to start looking at some actual physics, not just review stuff. So, if you've printed out your notes on describing physical phenomenon, be forewarned, we are not going through all of this in one go. That's not the point here. The point here is just to have all the material in one set. So, describing physical phenomenon. Before we start talking about motion, let's first understand the parts of physics that we're looking at. Physics is divided up into several main branches, such as electromagnetism, waves and optics, fluid mechanics, thermodynamics, nuclear physics, quantum physics, and what we're starting today, which is mechanics. And there goes the clock. Mechanics. Mechanics is the study of motion and the forces that cause that motion. And mechanics can be broken down into two subtopics. The first one is called kinematics. K-I-N-E-matics. Kinematics. It's the study of the mathematical description of motion. In other words, we learn how to describe the motion using equations. Then the other branch of mechanics is dynamics. And dynamics is the study of the forces that cause the motion. In other words, it's the explanation. So kinematics is the description and dynamics is the explanation. Now, which one are we starting? Well, we're going to start with kinematics. That's because if you have a physical phenomenon, you must first be able to describe the phenomenon which you're observing before you can even start to explain it. So kinematics first, then dynamics. Okay, so mathematically, how can we describe motion? Well, there are two types of quantities that we can use to describe motion, and they're very similar, yet they can actually be very different descriptions. What I'd like you to do is just take your pen or pencil and just make a line down the middle of the page because we're going to separate these two sides. One side is going to be the scalars, the other side is going to be for the vectors. So, let's begin. First, let's define what a scalar is. A scalar is any quantity that is described only by its magnitude. Now, magnitude is just a fancy word for the size of an object, for the numerical value that tells us how big it is. Okay? For example, if we say a car travels at 55 miles an hour, 55 miles an hour is the magnitude of the motion. It tells us how big the speed is, 55 miles an hour. On the other hand, you could describe the motion with a vector quantity. So how is that different? Vector quantities also have magnitude. They have size or numerical value to represent size. Okay? But they also have one more thing that scalars do not. Vectors have direction. They point. Okay? For example, if we said a car travels 55 miles an hour north, the 55 miles an hour is the magnitude and the north is the direction. Okay? Now, there are numerous examples of both scalars and vector quantities in physics. Let's name a few. Some scalar quantities that we use in physics would be time, distance, speed, energy, and even mass. These are all quantities that are described by a size or magnitude only. They don't point, in other words. On the other hand, some examples of vector quantities that we'll be using in physics would be displacement. Displacement, velocity, acceleration, force. Those are just a few examples of the types of quantities that are vectors. They have both a magnitude, a numerical value to describe their size, and they also have a direction. Okay? Now, how do we use these to describe motion? Okay, well, the first step into describing motion is you first must be able to describe the location of the object. That's very important. If you can't describe the location, it's going to be very difficult to do much else. So let's take a look at the scalar location of objects. The scalar location is called the place of the object, and X marks the spot. We use an X to represent the place, and it's just a magnitude only. For example, X equals 3 meters. Okay, so if something is located 3 meters away, you know how far it is, where its location is. However, how do we do the same thing with a vector? Well, with a vector, it's called position. And in this case, it's still X because X marks the location, but we're going to put a little sideways check mark over it. That indicates that that is now a vector quantity. So, a position not only is going to be how far away something is, but it's going to be in a direction. For examples, we could say 3 meters north. Okay? So that could tell you how far away the object is and in what direction it is located from you. Okay? And there is a difference here. Think about it. If you just said the object's 3 meters away, well, there's a 360-degree circle at 3 meters all around you. Where exactly on that circle would it be? Well, that's where vectors get more specific. If you say north, you know exactly where on the circle it is. All right, now let's suppose that an object is located at some initial location and then it changes location. All right, so what do we do if the object undergoes a change in location? Well, on the scalar side, you would undergo a change in place. Another name for change in place is distance. You can denote distance by delta x, change in place, or with a d. Either one is acceptable. They're both synonymous variables. So delta x or d are interchangeable. Okay, now, so let's say the object moves to a location 5 meters away, where it travels 2 meters. We would say the distance it traveled or change in location, the change in place is 2 meters. But here's the interesting thing. Distance can be measured along any shape path, okay? So let's say your initial place is here and your final place is here, and you go this way, all right? The path length is the distance traveled. Okay, the path length is the distance you traveled to get from your initial to your final position. Okay, now let's look and see how we would do the same thing with vectors. With vectors, a change in location or change in position is called a displacement. You've displaced from where you were. We can use a delta x for change in position with a vector symbol on it, or we can use a D with a vector symbol on it. Again, those are interchangeable, both mean displacement. But in this case, displacement is more specific. So whereas if you have an object that starts with some initial position and it ends up at some final position, regardless of the path taken, the displacement goes along a straight line from beginning to end. So that is the displacement of the object. Doesn't matter how far along the path the object traveled. The distance makes no difference. The displacement is always from the beginning to the end point along a straight line in a particular direction. So we use an arrow. Okay? All right. Now, what happens if we look at how fast we changed our location? Well, first we have to look at one new term, and this is a very important term, and this is a term I wish they would actually teach you guys properly in math class, but they don't. And that term is the term rate. Anytime you talk about a rate, you are talking about a ratio that specifically has time in the denominator of that ratio. Now, there are all kinds of rates in physics, and they're not all speed and they're not all velocity. There are many types of rates, but they all have time in the denominator. So how do you distinguish between one rate and another? By what's in the numerator. For example, power is a rate. It is the rate of work done. Okay? Electric current is a rate. It's the rate of charge flow. Q represents charge. So there are numerous rates in physics. They all have time in the denominator. And what distinguishes one rate from another is what's in the numerator. Okay? All right. So now let's look at motion rates. We're going to look at rate of change in location. So on the scalar side, if we are talking about rate of change in distance, all right, then we're talking about the speed of the object. And speed in physics does not use an S. Okay? It uses a V without the vector symbol, or you can just write the word speed. Okay? But be careful about using the S, because in AP Physics, as you'll find, some of you will find out later on, S can actually stand for a measure of distance, like around an arc length, around a circumference. So be careful about that. We need to use a V for speed, or simply write the word speed. Okay? Since it is a rate, V would therefore be a ratio with time in the denominator. And since it's the rate of change in place, we can write a delta x. What else could we write? Well, since d and delta x for distance are interchangeable, we could also write it as d over t, which is what you're more familiar with, I'm sure. Okay, so that's the rate called speed. Now, what if we look at it in terms of vector quantities? Well, if we look at the rate of change of position, we call that velocity, and it has a direction, and we need to use the letter V with the vector symbol on it, okay? Since it is a rate, that means it's a ratio with time in the denominator and change in position in the numerator. Or, since change in position is also displacement, we could substitute the displacement d right there. Again, you're probably more familiar with that than the delta x. Just remember, Delta x is delta is a symbol that means subtract. So delta x means mathematically x sub f minus x sub o. Where you are now minus where you used to be. Always final minus initial. Okay? Now, believe it or not, we're going to stop right there for today because there's another video that I would like you to watch today. It's from the Flipping Physics website with Dr. Palmer. He's a really interesting guy, you'll find out. And he is going to be teaching his 3 students, Bobby, Billy, and Bo. And I can't wait to see what you think of them, okay? But the video that you're going to watch is going to give you a very good idea of the difference between distance and displacement, okay? Thanks for listening. Bye-bye.